Okay, we'll get started with today's class. One thing I want to remind you about is if you're going to participate in the clicker questions, which will be the way that you will get your bonus points throughout the semester. Probably starting on Wednesday, we're going to do sort of some trial runs with the clickers just to make sure that it's working for everybody, including myself, since I'm new at this as well. So please, if you have them, bring them on Wednesday. If you're interested in getting it set up, now is a good time to do that. And we'll make sure that it's working for you to record your answers and that the answers get actually uploaded to Blackboard like they're supposed to, because that's how I'll be keeping track of your scores, especially on the bonus quizzes when they count. All right, so we'll start with that on Wednesday, but again, they won't count for your grade, at least not yet anyway. So we'll get there eventually. Okay, so today we're going to talk a bit more about atomic structure and how we classify different atoms from one another and the way the subatomic particles arrange themselves. So we talked about subatomic particles last time and some of the key experiments that were done to unveil their existence, particularly for protons and electrons. We didn't talk in detail about neutrons or how we discovered them, but they are an important subatomic particle nonetheless. So we'll start by reviewing what we did at the very end of last time. So the first slide of this lecture is going to be identical to the last slide of the previous one, and we're just going to give you a quick overview of the three subatomic particles and things that you need to know about them. Now, a lot of the numbers I give you don't need to memorize, but it does help to contextualize the differences between these particles and how small they are in reality and how relatively their size compared to each other. So the important one to know for today and for most of this course is the relative charge of the particles. So we have protons, neutrons, and electrons. Protons are +1, neutrons are 0, electrons are -1. So those are the three charges of the subatomic particles and that we're going to be going over. And then they have also, we should be aware of the abbreviations which I've given you here. P+ for proton, N0 for neutron, E- for electron. I'll be using that a lot, so don't be confused. The absolute charge is in coulombs. So coulombs is the SI unit for charge. There is information in the review chapter about SI units that you should be at least a little bit familiar with. So coulomb is what we use for charge, and a coulomb compared to a single proton or single electron is a huge unit. So if you want to put the charge of a proton or a neutron into units of coulombs, it's a very small number. 1.6 times 10 to the minus 19. Neutron, of course, is 0. It has no charge, and then the electron is exactly opposite of that. So very small in terms of coulombs. These individual particles are tiny. They don't carry a lot of mass or a lot of charge on their own, but when we're talking about collections of substances, we're talking about huge collections of these subatomic particles. Then the mass is also important, and specifically for what we're going to talk about today as well. And the relative mass is given in a unit called AMU, which is atomic mass unit. So if we want to just define the mass of one atom, it's convenient to do that with this unit because otherwise it would be an extremely tiny number. So in terms of AMU, the relative mass for a proton is 1, or just about 1. There are some decimal places on there, as it turns out, but we're not going to worry about that. But it's pretty much 1 if you round it. Neutrons, same thing. To a good approximation, they're the same mass, protons and neutrons. And as it turns out, as we'll learn today, we essentially think of all of the mass for an atom coming from the protons and the neutrons, which are in the nucleus. So the electron has a defined mass, but it's so tiny that we don't even worry about it. So the relative mass of an electron is, in AMUs, is 0.000549. So 0.000549. So way smaller than the protons and the neutrons, so effectively not contributing to the mass of the atom on the whole. If you want to know what these numbers are in grams, which is the SI, or I guess kilograms is the SI unit, but grams is more commonly used in chemistry, 1.67 times 10 to the minus 24 grams. So you need a lot of protons just to have 1 gram of mass. And then neutrons to 3 significant figures are the same. If you were to go more precise, there'd be slight differences. And then electrons, 1,800 times smaller, 9.11 times 10 to the minus 28. All right, so we learned this last time, and it's just a quick review of the subatomic particles and the individual characteristics of them. But what's more important is how they arrange themselves in different ways to make atoms and ions, which is going to be the subject of the first part of this course. So we're going to go into more detail now about atomic structure and how we classify atoms based on the number of these subatomic particles that are present. So if we want to think about what distinguishes one element from another, we talked about in atomic theory that elements are made up of atoms and that all of the atoms for a specific element must have the same mass and many other characteristics the same. Now that statement is partly true, but what really distinguishes one element from another in the atoms that make them up is the number of protons in the nucleus. So if you know how many protons are in the nucleus of an atom, you know what element that atom belongs to. So even though we can have slight differences in other regards for atoms of a given element, the protons in the nucleus have to be the same. So if you have an element of carbon, we'll learn that that has 6 protons in the nucleus. And every single carbon atom in the world will have 6 protons, no exception. So to characterize elements based on their atomic composition, we use what's called an atomic symbol. And this is going to tell us, in some sense, how many protons, electrons, and neutrons are in the atom that make up that element. At least not necessarily directly, but at least indirectly. So the anatomy for an atomic symbol looks like this. You have the symbol, which we'll talk a lot more about going forward, which is going to represent the name of the element. You have a numerical parameter A, which goes as a superscript, and then you have a numerical parameter B, which goes as a subscript. So 3 parts to the atomic symbol that you want to become familiar with. All right, so X is the atomic symbol, as I said. And this is a 1 or 2 letter abbreviation that tells you the name of the element. It's an abbreviation for the name of the element. Now, as we warned you about before the PA exam in those documents, and it's going to still be true for the course, you're responsible for knowing how to match the names and the symbols for the first 36 elements on the periodic table. We'll talk more about the periodic table going forward, but there are 36 of these that you'll sort of have to know in some sense, where you'll have to be able to match the name to the symbol and vice versa. So the first letter is capitalized in all of these, and this again just identifies the element for you. So if it's a 2-letter symbol, only the first letter is capitalized. Now the other 2, which are more important to really talk about in terms of atomic structure, this symbol just tells us what the historical name for the element is. There's nothing systematic about the symbol. It's just, some of them have Greek origin, some of them have Latin origin, some of them are named after people, some of them are named after places. So the name of the element and its symbol is not systematic in any way. But these other 2, which are numerical parameters A and Z, are very closely related to the structure of the atom and are systematic in how we define them. So Z is what we call the atomic number. So that's going to be the bottom number here. And this is that key characteristic that defines the identity of the element, which is the number of protons in the nucleus. All right, so this term here, Z, is going to tell us the number of protons, which of course is related then to the identity of that element. And then the parameter A that goes in the superscript is what we call the mass number. This will always be a whole number, and it's just a counting number, the number of protons plus the number of neutrons in the nucleus. So it's just the sum of the 2, protons plus neutrons, and it tells you then the full composition of the nucleus. So between these 2 numbers, Z and Z and A, you can know how many protons are in the nucleus, and you can know how many neutrons are in the nucleus. You can know both of those. The other term we need to define, and this is where we're going to reveal the one little thing about the atomic theory that's not quite correct, is the idea of isotopes. So isotopes are atoms of a given element, so they're all the same element when you're talking about isotopes. But they differ slightly from one another. And in the way they differ, they cannot differ in the number of protons. Remember, all atoms of a given element have the same number of protons, but they differ in the number of neutrons in the nucleus. And because they have different numbers of neutrons, they also have different masses from one another. And this is where Dalton was at least slightly wrong. I don't want to bang on him too much because he So we got it mostly right. But remember, what part of the atomic theory that we talked about last week was that all atoms of a given element have the same mass. Well, that's not exactly true. So they have the same number of protons, but they can have different numbers of neutrons, which of course, remember, the neutrons are just as massive as protons, so that can then give you different masses for different isotopes of the same element. Now, the reason that people didn't really initially realize that isotopes even existed is because the properties of the isotopes for a given element are generally almost identical to one another. So if you have two different isotopes of carbon, there are two different isotopes of carbon that exist naturally, you can't really tell them apart chemically. They react exactly the same, they look exactly the same, they behave exactly the same. So the properties of isotopes for a given element are almost identical, and that's one of the reasons why it took a while for people to even realize that they were there. Also the fact that people didn't even know about neutrons until much later, so that was also contributing to the lack of recognition of this possibility early on. Okay, but we now know that there are isotopes that can exist for elements. So the properties of isotopes for a given element, though, are nearly identical. So most elements that are naturally occurring, those that we use to make all the materials that we use in our daily life, they will mostly have multiple isotopes present at one time. There's very few elements that only have a single isotope that exists. All right, so the properties, though, are very similar for them. So some examples of isotopes would be hydrogen, the simplest atom on the periodic table. So hydrogen, the symbol is H. And remember, the bottom number here in the symbol is going to tell us the number of protons. So hydrogen always has one proton in the nucleus. That's the simplest nucleus you can have. And then for the most abundant isotope of hydrogen, it has 0 neutrons, which means it's going to have a mass number of 1. So this is one isotope of hydrogen. We have symbol, we have atomic number, we have mass number. And so this particular one is going to have 1 proton and 0 neutrons. So this is the only nucleus that doesn't have any neutrons in it. All the rest of the nuclei that exist in the world have at least 1 neutron. But this particular one has 0 neutrons, so it's going to have this atomic symbol. But we have 2 other isotopes of hydrogen that have been observed. So there's one that occurs naturally in very small amounts, which we call deuterium, although it's just an isotope of hydrogen, it's not a different element. And again, the symbol tells us it still has 1 proton. So all the isotopes for a given element have the same number of protons. But in this case, because the mass number is 2, that means we have 1 proton plus 1 neutron to give us a mass number of 2. And so they differ. This has now 1 neutron instead of 0 for deuterium. So if you've heard of heavy water, that's a form of water that has deuterium instead of hydrogen in it. And there is some naturally occurring deuterium, even in regular sources of water or other compounds that have hydrogen. Now the third one, which I don't believe is naturally occurring but can be prepared in the lab and is very important, especially for biological experiments, is what's called tritium. Okay, so this has the symbol H with a 1 and a 3, and again, 1 proton because it's hydrogen, it has to have the same number of protons, but with a mass number of 3, that means you have to have 2 neutrons this time. So 3 different isotopes of hydrogen, where the only difference between them is the number of neutrons in the nucleus, same number of protons as well. And this one, as it turns out, is not a stable nucleus. It will decay via a radioactive process, something you'll learn a lot more about in chemistry too. But all 3 of these do exist for hydrogen, and can be observed. Okay, so that's sort of the definition of isotopes, and we should realize then that the atoms for a given element do not have to have the same number of neutrons. There can be different numbers of neutrons for different atoms of that element. So let's look at a couple of examples of this and just the type of problems you'll have to do either on the homework or the test in the future. So we want to know the number of protons, electrons, and neutrons in the 2 most abundant isotopes of palladium. All right, so I gave you the symbol here for the 2 most abundant isotopes of palladium. It's if any of you are getting married soon, this is a common metal used in engagement rings. It's a little bit cheaper than gold and platinum, which is why it's popular now. Anyway, with that aside, most of you are too young to get married, so don't worry about that part of it. But palladium has 2 isotopes that are present in nature, 106 and 108. So if we want to know the number of protons, neutrons, and electrons in this, protons and neutrons come directly from the symbol. So the number of protons is just this number here, 46. So we gave you the symbol, so you just have to read that number off to get the number of protons. There's nothing more to it. The number of neutrons you're typically going to get indirectly because none of these numbers in the symbol exactly tell you the number of neutrons. Remember that top number, which is 106 in this case, is going to tell you the sum of the neutrons plus protons. So if we want just the number of neutrons, we have to take that number, which is the mass number, and subtract out the number of protons. Okay, so that's our first one, and then this is going to be our second, which is 60. So there are 46 protons and 60 neutrons. When you add those two numbers together, you get 106, which is the mass number for that isotope. Fairly simple. Now the one that we haven't talked about exactly yet is the number of electrons, but again, this one is very simple to get. So all atoms, unless there's, for a neutral element, have no charge. So if they have so many protons in the nucleus, they have to have the exact same number of electrons to balance the charge, because as we talked about at the beginning, the charge of protons and electrons are equal and opposite each other. So if we have 46 protons, we have to have exactly 46 electrons. So for any neutral element, again, no charge here, we're going to talk about ions in a second, but for any neutral element with no charge, there has to be the same number of protons and electrons. So that just comes from the atomic number 46. So if we go to the other isotope of palladium, we could do the exact same calculations, the exact same arguments to get those numbers. But remember, it's the same element, so that means it has the same number of protons. We don't even have to think about that. So it has the same number of protons. It's still neutral. We're not indicating any charge here on this. We'll talk about charges in a second. If there was a charge, it would be to the right of the symbol. So there's no charge. It's the same number of protons, so it has to have the same number of electrons, and it's still 46. So this other isotope of palladium, which exists naturally, will have the same number of protons and electrons. And the only thing that's different is going to be neutrons. So this time the mass number is 108 instead of 106. So when we subtract out the protons from that to give us how many neutrons there are, it's going to be 62. All right, so the only difference between these two is 2 more neutrons down here. That's it. And anytime you have 2 isotopes, it's only going to be differing in the number of neutrons. Okay, so that's how we take an atomic symbol and decompose it into the number of protons, neutrons, and electrons. And of course, you may have to do the opposite way, which is if we tell you an element with a certain number of protons and neutrons in the nucleus, what is the proper atomic symbol for that? So now we're working backwards, essentially. And remember the anatomy for an atomic symbol. We have the abbreviation, or the symbol in the middle, and then we have these 2 numbers on the left, where Z is the number of protons. This is typically the easy one to get at. And here we're telling you directly in the problem that we have 34 protons, so that's going to be Z, which is the number of protons in the nucleus. And then A is going to be the number of protons plus the number of neutrons. That's what we call the mass number, the total mass of the nucleus, and AMU is another way to think of that, or at least to approximate that. And so we have 34 protons. We have 43 neutrons. That's told to us directly in the problem. And so that means our mass number is going to be 77. So if we write the symbol out for this element, which has, we say the symbol is Q. There's no real element that has Q as its symbol, but in this fictitious world there is. And then it's going to have an atomic number of 34, which goes on the bottom, a mass number of 77, which goes on the top. All right, so we should be familiar then with these atomic symbols and how to then determine the number of subatomic particles based on the symbol. All right, any questions on that before I move on? All right, so this is fairly basic, should be a review for most of you. But the next one we want to talk about are ions. And ions are going to be a very important part of this course early on. We're going to talk first about individual ions, and then we're going to eventually talk about what are called ionic compounds, which are different ions combined with each other to make compounds. So if we have ions and we want to know the number of subatomic particles in an ion, we have to sort of define things and then realize that the only difference between ions and neutral atoms is the number of electrons. So for neutral atoms, as we just got done telling you, they have equal numbers of protons and electrons. Not necessarily neutrons, but equal numbers of protons and electrons. So in the examples we saw with palladium, 46 protons, 46 electrons. Neutral carbon would have 6 of each, and so on. So if you have a neutral element, neutral atom, you have to have equal numbers of each to balance the charge, because they have equal and opposite charges. When we form ions, what we're going to be doing is either removing or adding electrons. And this is really the substance of what chemistry is all about. So chemistry deals with moving electrons between one species and another. We're not going to change the nucleus at all. So to form ions, we just remove or add electrons, and we don't change anything else. It's tempting sometimes, if you see an ion, to think, oh, it might have either more protons in the nucleus or less protons in the nucleus. But remember, if we were to change the number of protons, we're changing the identity of the atom. We're not just making an ion from that. So when you're forming ions or trying to figure out how many subatomic particles are there, you're never going to add or remove protons. And this is related to part of the atomic theory, which is that when you have a chemical reaction, you don't change the identities of atoms. Okay, we keep all the conservation of mass, and we keep the identity of the atoms the same, but the electrons are going to be what's moving around. So you're going to move electrons from one atom to another when you form compounds, and that's what we're going to learn all about at the beginning of this course. But we don't ever touch the number of protons in the nucleus or the number of neutrons when we're doing chemical reactions. That's not to say it can't be done. You will learn in chemistry too about what's called nuclear chemistry, which is actually doing changes to the nucleus to change one element into another. That is possible in some situations. But for a normal chemical reaction, you don't change anything about the nucleus, and including when you form ions, you're not going to add or subtract protons, you're only going to add or subtract electrons. So then how many electrons do we add or subtract? Well, we're going to know the charge of our ion, and that's going to be determined by whether there are extra or deficient electrons. So if you have negative charges in your ions, you're going to add 1 electron per negative charge. So if you have a -1 ion, it's going to be just a single extra electron. If you add 2 electrons, you'll get a -2 ion, and so on. Negative charge, not change. And then if we have positive charges, of course we're going to subtract electrons then to give a net positive charge. So the key difference then between an atom and an ion is that in an atom, the number of protons and electrons have to be equal to balance the charge. In an ion, they will not be equal. You'll either have extra electrons or extra protons, whether the charge is negative or positive, respectively. All right, so let's see how this works in some real examples. So I gave you some atomic symbols now, and the only difference here is that our atomic symbol now includes charges. So we have the same numbers on the left, atomic number, mass number, but now we have this number superscripted on the right, which is going to denote the overall charge of that. So now it's an ion instead of an atom. It has a net charge to it. Iridium 3+, that's what this is called. That's my favorite ion in the world. Well, it forms a big part of my research group, so that's why. But it is a special ion to me. And we're going to talk now about the number of protons, neutrons, and electrons that are in an iridium 3+ ion. So for the protons and the neutrons, it's exactly the same as what we saw before. Remember, for ions, we don't change that. We just look at the atomic number and the mass number, and that's going to give us protons and neutrons. We don't have to worry about the charge when we're doing the nucleus part of it. So the protons and the neutrons in the nucleus we get the same way. We have 77 protons because, as the symbol tells us, the atomic number, the number is 77. That's his bottom number here. And then the number of protons and neutrons, again, comes from the mass number. So the sum of the two is equal to the mass number, which is going to be 192 for this ion. And when you form ions, you don't appreciably change the mass because the mass of an electron is tiny. So if you're adding or subtracting electrons, you're not going to change the mass of the ion just by adding a few electrons or subtracting a few. So the mass number is still 192. It's just the sum of the protons plus the neutrons, no different. And so the number of neutrons is just going to be 192 minus 77, which is 115. One trend you'll see, which we won't really talk about in detail, but you may notice, is that as you get to heavier and heavier atoms, that is atoms that have more and more protons, there tends to be more of an imbalance of protons and neutrons. So this one has a lot of extra neutrons, whereas the lighter elements tend to have equal numbers of protons and neutrons, or just maybe one extra neutron. That's not something important though, but that might be something you notice, and there's nothing weird about that. That's a behavior of atoms that you'll talk about much later on. All right, and then finally the number of electrons. This is the part that is new to us when we're talking about ions. How do we find the number of electrons? So we know that in a neutral atom there would be the same number of protons and electrons, 77. So the neutral ion has 77 electrons, but because it's a plus 3 charge, we have 3 less electrons. So 77 minus 3 is 74. So that's the number of electrons that we have. So to get this plus 3 charge, we have 3 less electrons and protons, so there's a net 3 extra protons or a plus 3 charge. Okay, so that's how it works for positive ions. We have to subtract out the charge to get the number of electrons that are present. And then for negative ions, it's very similar. We're going to add extra electrons this time. So if we have the sulfur 33 2 minus anion, we go here to find the atomic number. That gives us the number of protons, which is still 16, which it will be for any atom of sulfur, any ion involving sulfur. The number of neutrons is again just the mass number, which is 33, minus number of protons. Sorry, that's the mass number, not the number of neutrons. That's A. Okay, so we have 17 neutrons, so we don't do anything different for the nucleus, but then for the electrons, we have 16 protons in the nucleus. We have a 2 minus charge, that means we have 2 extra electrons. 16 plus 2 is 18. Alright, so again, we're adding 2 because of the 2 minus charge. Alright, so that was to some extent covered on the PA test, so it should be a review for most of you here, but review that if you have any problems with that. But that's sort of the first part of defining, the behavior of ions and atoms and all those things. So a couple more things related to this. We should be vaguely familiar with this document called the periodic table. We're going to use it a lot in this course. And you can use the periodic table to help you find the number of protons in an element. So we're going to talk a lot more about the structure of the periodic table later on, but just so you know, this is an option you have at your disposal. So if you look at a typical entry in the periodic table, it's going to look something like this. You have the atomic symbol in the middle, and then you have some numbers above and below. Now, as I'll show you here in a second, the periodic table that we use looks a little bit different. We don't have the name of the element, and so this is why. So here's the one that I just showed you, the carbon there. We don't tell you the name. It doesn't have the name of the element on here, so that's why we expect you to be able to match names and symbols for the first 36, because you'll always have this periodic table available to you, but if we give you a problem that says something about carbon, you need to know that the symbol for carbon is C. So your periodic table doesn't have the name of the element, but it has all the rest of the information exactly the same as I'll show you in this slide. Okay, so going back to that, if we have this entry in the periodic table, we can find then the number of protons by just looking at this top number here, which is the atomic number. This number here we'll talk in more detail about later on. This is related to the mass number, but it's not exactly the same, and we'll define that more probably later this week. So we'll cover this later, so don't worry about that. But if you want to know the number of protons in the nucleus, that's very easy to get from the periodic table, and something that can help you out as you go forward. Now, one more note I want to cover, and one of the reasons for having this in here right now is to realize something about how we write atomic symbols. So this term here, Z, which is the atomic number, this is usually left out of the atomic symbol. So the complete atomic symbol will have Z included in it. You should be familiar with that notation. But in more conventional nomenclature that chemists use, we don't usually put Z into the atomic symbol. So as an example with carbon, the most abundant isotope of carbon is carbon-12, which would have this full symbol. But more often than not, we're not going to include Z in the symbol. If we want to denote the carbon-12 isotope, we would leave out Z and just write it as 12C like this. Okay, so this is the more common way. So if you see these types of symbols don't be confused or think they're anything different. It's just that very often Z is left out. Now the reason that Z is left out, so why is this the more common nomenclature? Is because Z is redundant with the symbol. So remember that symbol in the middle there, the C, tells you that it's carbon. And because it's carbon, it must have 6 protons. So having both of those there is not really necessary, because carbon will always have 6 protons, so there's not really a good reason to put a 6 there all the time. There's never going to be another atomic symbol of carbon where that number is not anything but 6. Okay, so that's why we don't often leave out, or don't often include Z. You'll a lot of times just see the symbol, which tells you the name of the element, and which indirectly tells you then the number of protons in the nucleus. So we aren't going to put that there all the time. All right, so be aware of that. One more type of sample problem we can do, which is just involves a little bit more thought, is determine which 2+ ion has the same number of electrons as Br-. So now we're going to get used to using the periodic table a little bit and how we can go back and forth with this information. So we want to know which 2+ ion has the same number of electrons as Br-. So we need to find out the number of electrons in Br- first. All right, I didn't give you the full atomic symbol here, so you're going to have to go to the periodic table to help you out and get used to doing this. So we have Br-. We know there's 1 extra electron, but we don't know how many protons there are. So if we go to the periodic table, and this is something we should become very familiar with, we find Br on the periodic table, and this number right above it, 35, tells us that there are 35 protons in the nucleus. Okay, so we go back here, we have 35 protons. We have 1 extra electron, so we have 36 electrons. And now we want to know what is the name of the 2+ ion, or the symbol for the 2+ ion, that has also 36 electrons. These are what are called isoelectronic ions. They're ions that have different charges but the same total number of electrons. All right, so if we have a 2+ ion that has 36 electrons, how many protons should that have? I heard one person say it. So there should be 38 protons. Okay, because a 2+ ion is going to have 2 extra protons. So if this 2+ ion has 36 electrons, it has to have 2 more than that 38 protons to give a +2 charge. And now we have to figure out which symbol that corresponds to. So we go to the periodic table and we find which element has 38 protons. We find atomic number 38, which is down here, Sr. This is not one you'd have to memorize the name of, but it's called strontium, and it's number 38 here on the periodic table. So that means if we want to write the symbol for this 2+ ion, I didn't specify anything about the mass number, so we would just do Sr 2+. Okay, so this is the 2+ ion that has the same number of electrons as Br-. We will come back to ions in more detail when we start talking about ionic compounds, but this is something we should be able to do now that we can define the numbers of protons, electrons, and neutrons. And then here's one that's, in some sense, a nuclear chemistry type problem, although we're not going to really define it as such, where we have a lead 2+ ion, and we imagine that it loses 2 protons and 2 neutrons, which we call an alpha particle. That's what we talked about with the gold foil experiment last time. And if it loses 2 protons and 2 neutrons from the nucleus, what is the atomic symbol for the resulting atom or ion? Okay, so we're changing lead into something else because we're changing the number of particles in the nucleus. As I said, this doesn't normally happen in chemistry, but there are ways we could possibly do that. So if we write the symbol for 207 lead, 2+, we should also include the atomic number because we want to know how many protons there are in the nucleus. So this ion here, if we go to Pb on the periodic table, that's lead, that's down here, 82. So this is going to start with 82 protons in its nucleus because it's lead, Pb. So that symbol tells us that it has 82 protons. And so we want to know the number of subatomic particles that we're starting with. So the ion that we're starting with, 207 Pb2+, which is lead, has 82 protons. The number of neutrons is going to be this number, the mass number 207 minus 82, which if I can do that in my head is 125. So you have 82 protons and 125 neutrons. That comes from the left side of the symbol. And then we have a 2+ charge, which means we have a deficiency of 2 electrons or an excess of 2 protons. So we start with 80 electrons. Okay, so this is what we're starting with. And now we say we imagine some process where we lose 2 protons and 2 neutrons. So our new atom, or ion, or whatever it ends up being, is going to have 2 fewer protons. We lose 2 protons, so that's 80. We lose 2 neutrons, so that's 123. And we have the same number of electrons. We didn't say anything about anything happening to electrons, so we still have 80. All right, so again, we now know the number of subatomic particles in this new atom, so we can define the symbol just by working backwards. So we have to find out the name of the atom. So we have 80 protons, which means we can use that to figure out what the new symbol is. So if we go to the periodic table, number 80 here is Hg, which is mercury. So Hg has 80 protons in its nucleus. That's what that number tells us. So it's going to be Hg. If we add these two together, that's going to give us the mass number. 80 plus 123 is 203. So our symbol is going to have a superscript of 203 up here. And then if we look at the protons and neutrons, we now have 80 of each. 80 protons, 80 electrons. Sorry, protons and electrons, 80 of each. So we have no net charge in this atom now. So it's no longer an ion, it's a neutral atom. And so we can stop there, 203 Hg. If we really wanted to, we could also put the 80 down here to make it a complete symbol. But like I said, that's often left out. So that's going to be our new symbol. We just start with our initial ion here. We lose 2 protons, we lose 2 neutrons, and we write the new symbol that corresponds to that resulting product. Okay, so this is something we should all be able to do now, and you'll see a lot of problems like this likely on the first homework assignment, which is now available. That's something else I forgot to remind you guys of. The first homework assignment opened up on Sunday. Many of you probably noticed that, and I think some of you already attempted it, which is great. But you have 4 attempts to finish the homework. I think this first one only covers Chapter 1, which we're pretty much finishing today. So you'll have all the material after today to get through that. And it's going to be due at the end of the day next Sunday, 11:59 p.m. But I encourage you to get an early start on it. If you have any questions about the homework topics, please come see me or use one of the many resources that we have available. Okay, so after that quick aside, that little intermission, we're going to wrap up Chapter 1 with that, and we're going to move on now to something completely new, which is Chapter 2. So we've now talked about a lot of the early ideas about the structure of atoms, and we're pretty much all set now on the idea that we have a very dense nucleus at the center, which contains the protons and the neutrons. We have electrons that surround that. But one thing that people didn't really understand early on was, well, how exactly are the electrons arranged? Is it just a random cloud? Is there some structure to it? And so what we're going to get into in Chapter 2 is talking in more detail about the electrons and how they arrange themselves around atoms and the different theories that govern those, those ideas. And a lot of these early ideas came about in the idea of what we're going to talk about, which is called quantum theory, by studying the interaction of light with matter. Okay, so people were, a lot of people at the time thought that they had a pretty good idea of what was going on, and that this simple atomic theory was sufficient to describe everything, and classical physics was sufficient to describe everything, and we could just sort of wash our hands and go home, problem solved. But then some ambitious scientists started doing some experiments where they studied the interaction of light with matter, and they found some really weird observations that didn't really jive with what people thought was true. So again, the idea of the scientific method, you test an idea, you find something unexpected, you have to refine the hypothesis and come up with new theories to describe it, and that's what we're going to get into in Chapter 2. But before we talk about that, we have to understand what electromagnetic radiation, or what light is, to begin with. So today we're going to finish up by just talking about the properties of waves, and this is what makes up all of the light and electromagnetic radiation that people were using to study interactions of these with matter and coming up with these new ideas. So an electromagnetic wave is also referred to as radiation. You'll hear those used interchangeably. So when we talk about electromagnetic radiation, that's what we mean the same thing. And what exactly is it? So it's energy that's propagated by electric and magnetic fields that oscillate in intensity as they travel. All right, we're going to classify electromagnetic radiation and all types of it in more detail, but you know what a lot of these things are. So visible light, all the colors that we see are caused by electromagnetic radiation. X-rays, which you're certainly familiar with, at least in a medical context. Radio waves, I don't know if anybody listens to the radio anymore, but they're out there. And microwaves, which you often use to cook your food. So these are some examples of electromagnetic radiation. There's a few others, and we'll learn how to classify them later on. So this is kind of a picture of what it looks like schematically. So you have electric field, which is shown in blue, abbreviated with E. So you have an electric field that oscillates, goes up and down in intensity as it travels through space, and you also have the same perpendicular magnetic field that's associated with this, which is shown in red and is a perpendicularly propagated wave, which also oscillates in intensity. So that's why we call it electromagnetic. It has an electric field part and a magnetic field part. But the key part of this is that, this is a wave-like form. It has oscillating intensity, and we don't normally think about both components separately. We just think of a single wave in 2 dimensions is a more traditional way to think about this. So we have then certain properties of a wave that we want to be familiar with. Okay, so this is what it looks like in sort of a standing wave, what we call a standing wave. So one parameter that's very important is called the frequency. We're going to abbreviate this with nu, which is a Greek letter that kind of looks like a V with someone like blowing wind on it. It's a little bit tilted V. I'm not very good at drawing them, but that's what it is. Not a V, it's a nu. And this is what it's the number of cycles per second is a way to think about this. So the unit for frequency can be written as inverse seconds because it's number per second, or it's also named after a guy, Hertz, Hz, Hertz. So those mean exactly the same thing. There's no difference, but you'll see probably both of them in different contexts. So frequency is the number of cycles per second. When you look at a picture like this that we call a standing wave, so normally waves are moving through space. They don't stand still and allow you to just look at them like this, but we can think about if we take a snapshot of a wave moving through space, this x-axis here, this horizontal axis, we can think of it in either as being time or as being a distance length. So there's 2 different ways of thinking about this, and the 2 different parameters come from those 2 different ways of thinking about it. So let's imagine that this axis is time for a second, and let's say the space between these 2 crests here is 1 second. So let's say that represents 1 second in time, and the frequency then is going to be the number of cycles that oscillate through that 1 second. So we have 1, 2, 3, 4 complete waves in the span of 1 second. So the frequency of this would be 4 inverse seconds, which we would also write as 4 hertz. Okay, so that's the definition of frequency, the number of cycles that go by in 1 second. Now, probably a better way to think of frequency is imagine that you're standing still and you're watching a wave go past you. And as the wave goes past, and because it's a wave, the intensity is going to oscillate up and down. So it's the number of up and down oscillations in 1 second. So if you have a really low frequency and you're watching the wave oscillate in front of you, you'll be going up and down really slow, faster frequency, faster, 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 so on. So frequency is the number of oscillations per second as a wave travels right past you. That's another potentially clearer definition of that. Wavelength is a pretty straightforward one. So we have a parameter called wavelength. All right, another Greek letter. One thing you'll learn in this course that you didn't expect is the Greek alphabet. So we're starting early with nu and lambda. So wavelength is abbreviated with lambda, and it's the distance between equivalent points on a wave. And it's given in meters or some so it's a length. So it's the standard unit is meters, but it's often given in something like centimeters or nanometers, depending on the size of the wave you're talking about, the wavelength. So lambda can be defined in a lot of different ways. Now let's imagine that this horizontal axis is a length scale instead of a time. And so you take the top of one wave and you measure the distance to the top of the next wave. That's one way to define lambda. Or you could take the bottom of one wave, measure the distance to the bottom of the next wave. That's also the same distance, lambda. Or if you want to take the center point here, the node, if you want to call it that, and measure the distance between two successive nodes. Now it has to be a complete wave, so you would start here, go through one full wave and one full oscillation, get to here. That's also the same distance lambda. So you'll get the same result however you think about it, but it's the distance between two equivalent points on the wave. And that's what we call lambda, the wavelength. And then the last one, which is not terribly important for us, but we should be familiar with it, at least in terms of the conventional definition of waves, is amplitude. So this is the height of a wave crest. Which is related to the intensity of the wave. So amplitude would be, for example, this distance here, the distance from the center point to the top of a wave, or it could be alternatively the distance from the center point to the bottom of a wave, but it's that total height. And so that's related, at least classically speaking, to the intensity of the electromagnetic radiation. So if you had a really dim green light bulb, it would have a very low amplitude, but then if you shine a green laser, which is a very strong source of light, it would have a much higher amplitude. So that's just related to the intensity of the wave, but not anything else more than that. And we're not going to really use amplitude in anything that we talk about anyway. Okay, so those are the three properties of the waves. Let's take a little bit more detail and just compare two waves to each other now. So if we have two pictures of a wave, how do we compare their properties? So here I have two overlaid waves, A, which I'll have in blue, B, which is in red. And let's compare the wavelengths and the frequencies of these two. All right, so if we compare, let's look at wave A here. If we go peak to peak, remember lambda, or wavelength, is a distance between two peaks. So if we use these small divisions here, these small lines, which are a little bit faint, but you can see them, lambda, there's 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 of these small divisions in between the two peaks for A. So the wavelength for A in whatever these arbitrary units are would be 8. If we do the same thing for wave B, so now we have, for wave B, let's go over here and do it, two peaks for wave B. We measure this distance, it's going to be 1, 2, 3, 4 divisions. 1, 2, 3, 4 divisions for, and so the lambda for B would be 4. All right, so that means the wavelength for A is 2 times the wavelength for B. So in relative terms, A has twice the wavelength of B. So if we're comparing two waves, this allows us to do this. Now we know this relationship between wavelength. What's the relationship between the frequencies of the two? So let's go down here. Let's assume that this period of time represents 1 second. So let's look at the frequency then. Remember, we can think of this in two different ways. So wave A, we have 2 full cycles that span this period here. And then for wave B, we have 1, 2, 3, 4. So we have 4 cycles for wave B in that same period. And so the frequency of A is only 1/2 that of the frequency of B. So we see here there's this inverse relationship. The wavelength for A is 2 times the wavelength for B, but the frequency for A is 1/2 the frequency for B. So that's what's called an inverse relationship. If the frequency of one is higher, the wavelength is smaller, and vice versa. So that's an important relationship we'll come back to next time. The last thing we can talk about quickly is amplitude. Again, this isn't very important for this course, but if we want to measure amplitudes, the amplitude for wave A in this case, which is also in blue, we have a height of 2. Remember, that's the height of the wave, so the amplitude for A is 2. The amplitude for B would be from here to here, which is just 1 division, so 1. So that's just a quick definition. We'll come back next time to the relationships between some of these parameters and more details about the interaction of light with matter.